Now let's have a look at the interactions between gas and tissues. When a gas becomes into contact with liquid, a migration of gas molecules towards the liquid and vice versa occurs. This, for example, is the principle utilized to produce mineral waters and carbonated drinks. Let's consider a practical example. We place a liquid in an open container. A gas, air, acts on its surface. There is a state of equilibrium at the beginning since the pressure of the gas balances its tension in the liquid, and the molecules that enter are equal to those that are freed. Compressing the gas on the surface of the liquid, its pressure is increased. The difference thus created compared to the tension in the liquid causes a migration of gas molecules towards the liquid. This phenomenon continues until a new state of equilibrium has been achieved. This phenomenon can be compared to adding sugar in a glass of water and stirring it. The sugar goes into the solution in the water, just as the gas is diffused in the liquid. But if we continue to keep the pressure constant, we notice that the phenomenon stabilizes itself, and it seems like the passage of gas towards the liquid is interrupted. But what happened? Exactly the same thing that happens if we continue to add sugar. After a certain point, the sugar no longer dissolves and remains in a solid state. The water is saturated with sugar just as our liquid is saturated with gas. The only difference between a solution of gas and the example with the sugar is that the quantity of gas that can be dissolved is not constant. It varies according to pressure. At higher pressures, higher quantities of gas will be dissolved, and vice versa. The phenomenon of gas diffusion in a liquid affects divers. In fact, the tissues that make up the human body are composed principally of water. On the surface, the body tissues are in equilibrium with the atmospheric pressure. In scientific terms, we say that the tissue tension of dissolved gas is equal to the atmospheric pressure. Descending during a dive, the ambient pressure increases on the order of 1 atmosphere every 33 feet. But the tissue tension is lower, and according to Henry's law, tissues absorb gas. This absorption increases as much as the difference between ambient pressure and the tension of the gas in the tissue increases. This difference is called gradient. However, the phenomenon can also work the other way around. As external pressure decreases, the gas passes from its state in solution to its gaseous state, freeing itself, and this is where the problems start. Let's take a bottle of carbonated drink and open it. The pressure decreases rapidly as the liquid finds itself in a state of oversaturation compared to the environment. The gas in diffusion frees itself violently in the form of bubbles and foam. If, however, we open the bottle slowly, the phenomenon is markedly inferior, and the bubbles will be smaller and fewer in quantity. This is because the gas has time to free itself little by little. When descending at depth, the tissues of the human body absorb gas. Therefore, it is obvious that when returning to the surface, they must eliminate the gas that they absorb. The tissue tension is greater than ambient pressure, and again, according to Henry's law, the gas molecules migrate from their state in solution to the gaseous state. If we ascend very rapidly, the gradient between tissue tension and atmospheric pressure will be higher, and our bodies will tend to end up like the bottle of carbonated beverage, with disastrous consequences. But if we ascend very slowly, we allow the gas the necessary time to return to its free state without problems.